Let's talk about sound. You hear it every single day. Right now, you're hearing my voice. This morning, you heard your alarm clock screaming at you. You heard the coffee maker gurgling. You heard traffic outside, doors slamming, music playing, people talking. Sound is everywhere. It's so familiar, so constant, so ordinary that you probably think you understand it. You learned about it in school, right? Sound waves, vibrations, something about air. So you must understand it. Okay, explain it to me. When I speak, how does the information that I'm creating with my vocal cords get inside your head? What's actually traveling between my mouth and your ear? Most people will say something like, sound waves move through the air. Sure, fine. But what does that mean? What's actually moving? Is something traveling from me to you? And here's the thing that'll bother you. When you really try to explain it, when you dig into the details, you realize you don't actually know. And that's exactly where we need to start. Here's what everyone thinks they know. Sound is a wave. Waves travel. Therefore, sound travels. Simple, right? But hold on. What travels in a water wave? You watch an ocean wave, and you think water is traveling toward the shore. But drop a cork in the water. Does it travel to the shore? No. It bobs up and down. The water isn't actually moving horizontally. Only the pattern moves. The energy moves. But the actual stuff, the water itself, stays roughly in place. Now apply that to sound. When I talk to you, is air traveling from my mouth to your ear? Are the actual air molecules making a journey across the room? Think about it. If air was actually moving from me to you, you'd feel wind every time someone spoke. You'd feel a breeze hitting your eardrum, but you don't. So what's happening? Here's the uncomfortable truth. Most of what you think you know about sound is a convenient simplification. It's not wrong exactly, but it's missing the beautiful, bizarre, almost unbelievable mechanism that actually makes sound work. And when you understand that mechanism, when you really see what's happening, you'll never listen to anything the same way again. You'll realize that sound isn't just physics. It's a kind of miracle. So let's break down the question properly. When I speak, I'm creating sound. You hear it. Something must be connecting us. What is that something? First, eliminate what it's not. It's not a thing traveling. No little sound particles are flying through the air like bullets. That's not how it works. It's not the air itself moving in bulk from me to you. We established that. So what's left? Here's the key insight. What travels is a pattern, a disturbance, a choreographed dance of molecules where each molecule barely moves, but the pattern of their movement propagates through space. Imagine you're in a dark stadium and everyone has a flashlight. Someone starts a wave. Each person stands up, raises their light, then sits down. The wave moves around the stadium. But notice, no person travels around the stadium. Each person moves only up and down. Yet the pattern, the wave, travels horizontally. That's closer to what sound is, but it's more subtle than that. Because in a stadium wave, you can see the people. You can see them stand and sit. With sound, you can't see the air molecules. You can't see them moving. And the movements are so tiny, so unbelievably small, that if you could see them, you'd wonder how such microscopic vibrations could carry information across a room, let alone across a concert hall. Here's another way to think about it. What is information? When I say a word, I'm encoding information in a physical pattern. That pattern has to get from my brain, through my vocal cords, through the air, to your eardrum, through your auditory system, into your brain where it's decoded back into meaning. That's astonishing. The information doesn't exist as a thing. It exists as a relationship between things, as a pattern of energy distribution. And that pattern has to remain coherent, has to maintain its structure as it propagates through billions and billions of randomly bouncing air molecules. How does that even work? How does nature preserve information in chaos? All right, let's build this from the ground up. Start with air. What is air? It's not nothing. It's something. It's matter. Specifically, it's a gas made mostly of nitrogen and oxygen molecules. These molecules are not sitting still. They're flying around in every direction at about 500 meters per second. That's over 1,000 miles per hour. They're colliding with each other constantly. Billions of collisions every second. It's chaos, complete random molecular chaos. Now, in this chaos, there's an average pressure. The molecules are banging into everything with a certain average force. That's atmospheric pressure. It's not uniform at the microscopic level. At any tiny point, the pressure fluctuates randomly as molecules zoom in and out. But averaged over space and time, there's a steady background pressure. Now I'm going to speak. What happens physically? My vocal cords vibrate. There's stretched membranes in my throat that slam together and apart very rapidly. When they push together, they compress the air molecules directly in front of them. They shove molecules closer together than they want to be. That creates a region of slightly higher pressure. When the vocal cords pull apart, they create a region of slightly lower pressure, a rarefaction. So I'm creating alternating regions of compression and rarefaction in the air. But here's the key. Those molecules I just compressed, they're not happy about it. Why? Because when you push gas molecules closer together, they repel. Not because they're electrically charged, but because when molecules get close, their electron clouds repel. It's quantum mechanics in action. But forget the quantum part for now. Just know, molecules push back when you squeeze them. So the compressed region wants to expand. And when it expands, it pushes on the neighboring air, compressing it. Now that region is compressed, so it wants to expand, so it pushes on its neighbors. This is the propagation. The disturbance spreads. Each tiny volume of air pushes the next tiny volume. It's like dominoes, except the dominoes don't fall over. They just wobble and push their neighbor, and then they wobble back. The molecules oscillate back and forth around their average position. Each molecule moves maybe a few micrometers. That's millionths of a meter. Practically nothing. But that tiny movement, multiplied across billions of molecules, all choreographed in this wave pattern, carries information. The pattern moves at about 340 meters per second in air. That's the speed of sound. But remember, no individual molecule travels at that speed. Each molecule is flying around randomly at 500 meters per second. But the pattern, the organized disturbance moving through the random motion, travels at 340. That's remarkable when you think about it. Order emerging from chaos. Now let's talk about what determines the speed of sound, because this is where it gets really interesting. Why does sound travel at 340 meters per second in air and not some other speed? It comes down to two things: how stiff the medium is and how heavy it is. Think about stiffness first. When you compress air, how hard does it push back? That's determined by the pressure and the properties of the gas. Higher pressure means molecules are packed tighter, so they push back harder when compressed, so disturbances propagate faster. That's why sound travels faster in high-pressure environments. Temperature matters too, because hot gas molecules move faster, which means they transmit the push to their neighbors more quickly. At room temperature, sound travels at 340 meters per second. At freezing, it's slower. At higher temperatures, faster. Now the second factor, mass. Heavier molecules are harder to accelerate. If you try to push a bowling ball versus a basketball, which responds faster? The basketball. Same with molecules. Light molecules respond quickly to pressure changes. Heavy molecules respond sluggishly. Helium atoms are much lighter than nitrogen or oxygen molecules, so sound travels faster in helium. That's why your voice sounds funny when you inhale helium. The sound waves from your vocal cords travel faster, which shifts the resonant frequencies of your vocal tract higher, making you sound like a cartoon character. But here's something most people don't know. Sound travels even faster in solids, way faster. In steel, sound travels at about 5,000 meters per second, 15 times faster than in air. Why? Because solids are stiffer. Much stiffer. When you compress a solid, it pushes back way harder than a gas. The atoms are locked in a lattice connected by electromagnetic forces, and they really don't want to be displaced. So disturbances propagate very quickly. This is why you can hear a train coming by putting your ear to the railroad track long before you hear it through the air. The sound travels through the steel rails faster and with less energy loss. In water, sound travels at about 1,500 meters per second. Faster than air, slower than steel. Water is denser than air, which you'd think would slow sound down because water molecules are heavier. But water is also much less compressible than air. Squeeze water and it pushes back hard. That stiffness wins, so sound travels faster. Whales can communicate across hundreds of miles underwater because sound travels efficiently through the ocean. The density helps carry the energy, and the speed means information travels quickly. So every material has its own speed of sound determined by this balance between stiffness and density. It's a fundamental property of matter. And when you understand this, you realize that sound isn't just about air. It's about the mechanical properties of anything that can vibrate. Now let's follow the sound wave all the way to your ear. The disturbance propagates through the air as alternating compressions and rarefactions. This pattern hits your eardrum. Your eardrum is a thin membrane stretched across your ear canal. When a compression arrives, the pressure increases slightly, pushing the eardrum inward. When a rarefaction arrives, the pressure decreases, pulling the eardrum outward. So your eardrum vibrates in response to the pressure fluctuations. And here's what's amazing. The movements are incredibly small. For a normal conversation, your eardrum might be moving by nanometers. That's billionths of a meter. The diameter of an atom is about 1/10 of a nanometer. So your eardrum is moving by the width of maybe 10 atoms. And yet you can extract detailed information from these movements. You can distinguish between thousands of different sounds. You can recognize voices, you can hear music and extract melody, harmony, rhythm, all from nanometer scale vibrations. How? Your ear is an exquisite piece of biological engineering. Behind the eardrum are 3 tiny bones, the hammer, anvil, and stirrup. These bones form a mechanical lever system that amplifies the vibrations and transmits them to the cochlea. The cochlea is a fluid-filled spiral structure lined with thousands of tiny hair cells. Different hair cells respond to different frequencies. High-frequency sounds excite hair cells at the base of the cochlea. Low-frequency sounds excite hair cells at the apex. When a hair cell is stimulated, it fires nerve impulses to your brain. Your brain receives these signals and reconstructs the sound. It identifies patterns, filters out noise, focuses on relevant information. It's performing Fourier analysis in real time, decomposing complex sounds into their frequency components. And it's doing this continuously, automatically, without you even thinking about it. But here's the truly mind-bending part. The sound doesn't exist in your head. What exists in your head is electrical activity, nerve impulses, patterns of neurons firing. The experience of sound, what philosophers call qualia, is constructed by your brain. The sound wave in the air is just a pressure pattern. The vibration in your ear is just mechanical movement. The nerve signals are just electrochemical impulses. Somehow, from all of that physical stuff, you experience sound. You hear music. You feel emotion. That's the hard problem of consciousness, and nobody really understands it. But even setting aside consciousness, just the mechanical part is astonishing. A tiny disturbance in air pressure created by my vocal cords propagates through space as a choreographed dance of molecules enters your ear, gets transduced into mechanical vibrations, then into electrochemical signals, then into neural activity. And that neural activity corresponds to meaning, to words, to ideas. Information has been transmitted. Mind has connected to mind through the medium of vibrating air. Now here's what will really echo in your mind. Sound doesn't exist without a listener. I know that sounds like philosophy, but it's true. The pressure wave exists. The molecular vibrations exist. But sound as an experience, as a sensation, requires a brain to interpret it. If a tree falls in a forest and no one is around to hear it, does it make a sound? The correct answer is, it makes a pressure wave. It creates a disturbance in the air, but it doesn't make sound because sound is the conscious experience of that disturbance. Sound is what happens in your brain, not what happens in the air. This is what Feynman understood deeply. Physics describes the mechanisms. It describes molecules and pressure and wave propagation with beautiful mathematical precision. But the experience, the quality of sound, is something else entirely. It's the bridge between the physical world and the mental world. And we don't fully understand that bridge. Every time you hear something, you're experiencing one of the deepest mysteries in nature. You're experiencing the conversion of physical pattern into mental experience. Matter becoming mind. And it's happening automatically, continuously, right now as you listen to these words. The air between us is vibrating. Molecules are dancing. Energy is flowing. And somehow that energy is becoming thought in your brain. My idea is becoming your idea, not by magic, not by telepathy, but by the precise, mechanical, utterly astonishing process of sound propagation. That's what Feynman discovered and tried to teach us. The miracle isn't in some mystical realm. The miracle is in the physics itself. So when you ask how sound travels, the simple answer is through waves of pressure in a medium. But the real answer is so much richer. Sound is the story of how order emerges from chaos, how information survives in a universe trending toward disorder, how minds connect across space through the medium of matter. It's a reminder that the ordinary is extraordinary when you actually understand it. You don't need to invoke anything supernatural to find wonder. The natural world, understood deeply, is more wonderful than any fiction. Every conversation you have is a miracle of physics and biology. Every piece of music you hear is the universe computing solutions to wave equations in real time. Every sound is evidence that the world is comprehensible, that nature follows rules, and that we're capable of figuring those rules out. That's what Feynman wanted us to see. Not just the equations, not just the mechanisms, but the beauty of understanding, the joy of really knowing how something works. So the next time you hear anything, remember, you're not just hearing sound. You're experiencing the universe expressing itself through pattern and vibration, and that should echo in your mind forever.